All right, so we are ready for our last talk of this morning session. Who is going to talk now is Pablo Lessa from Universidad de Uruguay, Montevideo. He's going to speak about quasi-isometric free groups in SLR3.
So, does it work? Can you hear me? All right, good. So, thank you, Jacqueline. I want to talk about something which is a group theory, like in SL3R. But really, the questions are by analogy with well-known things in differentiable dynamics. And so I would like to take the opportunity, given the setting, to say 2 words about something which all of you know much better than me. So the analogy is via this concept, a very well-known concept in dynamics, which is dominated splitting. Dominated splitting. Right? And so the prototype result we would like to extend, not really extend, like make some analogies with, is like this super well-known result which appears in the work of Magnier on the C1 stability conjecture, which is, the setting is the following, right? You have a closed manifold. You have a diffeomorphism. And you consider the periodic points which are hyperbolic and have hyperbolic periodic points. Periodic points of index I. Right? So the periodic points where all the eigenvalues of the differential when you return are outside of the unit circle, and you have I of them which are inside of the disk. Okay? And so the theorem, which I think is, so I was reading Magnier's paper yesterday, and I think it's actually by Pliss in 72. And also, it was discovered independently several times, and so Magnier proved it in 74. And then Liao also proved it. Okay. And so the theorem, which probably most of you know about, is that if F, your diffeomorphism, is in the interior of the set of diffeomorphisms with all periodic points hyperbolic, points hyperbolic. That's a set. So you perturb F C1 and it still has all the periodic points hyperbolic. Then if you pick any index between the 0 and the dimension of M, for 0 and M, okay, also, but it's a bit different. There is a dominated splitting on the set, the closure of the set of periodic points. It admits a dominated splitting. There is a dominated splitting. An invariant dominated splitting. On this set. Okay. So this is, I think this is like the starting point for the C1 stability. And so probably all you guys know about this dominated splitting. What it means is that you can choose for the points on the set, on this set, you can choose EX and FX, which add up to the tangent space, the dimension of E. It's continuous. It's actually a consequence, but okay, continuous. Dimension of E is I, right? And then there's some ugly condition, which is the, okay, I can write it. But it is that if you look at the differential of F restricted to E, and then you look at the differential of F minus N restricted to F of X, Mx, restricted to F, then this goes to 0 really fast. That's C lambda to the N, C positive, and lambda between 0 and 1. So for all X and for all N, you get this thing. And what it says is that, for example, your periodic points, when they come back, there's actually like a uniform exponential in N, contraction on the stable and in the unstable. Sorry, I didn't mean that. I mean that what it says is that when you come back, you have a uniform contraction of the angles towards the subspace. F is the unstable in this case, so F. All right. And so this is just the thing that I think I should say here. And now we're going to do analogy to group actions, but we didn't do it. It's actually Sullivan. So keep breaking the chalks. I'll write this thing scorecard. All right. All right. So, sorry. Okay. So there's this paper by Sullivan, which is not the same paper that Francois was mentioning in his talk. So it's 1985. And it has this really intriguing, he says this is a scorecard, and it has 2 columns and 2 rows. I think it's an instance of this dictionary. And so the columns are already very interesting. It says here, Kleinian groups. Oops. Okay, I shouldn't have done this line. Kleinian groups. And here it says rational maps. Maps on C hat. Sorry. Should be legible. And the rows are also like super interesting to me. So the first row says, sorry, it says stability. So structural stability implies hyperbolic. And the other thing is structural stability. Also stability, I just wrote stability. Is open and dense. Okay. Oh. All right. So this is legible? All right, cool. All right, and the paper says, so this is what he writes. He writes, yes, this paper, the paper I'm citing, 1985. That's what it says, okay. Here it says, yes, Mania Sullivan. And here, with question marks. And so I want to say what he proves, and then we can talk about higher rank. So what he proves is the following. And I will show the connection to this dominated splitting. But what he proves is the following. So Sullivan defines for a subgroup gamma in PSL2C. Right? So it's 2x2 matrices with complex entries, and so there are Möbius transformations of the Riemann sphere, right? So and he defines 3 things. So one of them is structurally stable. This is his analogy to the Diffio case. He says it's structurally stable if all representations. Okay, I should write like rho isomorphism from gamma to PSL to C. Near the inclusion, are faithful, injective, right? Faithful. All right? So that's his definition of structural stability is that nearby groups are actually isomorphic to gamma. That's a definition. And then he has two more things, which I should write. And then the rigid, if they are all I'll conjugate to the inclusion. So this is like a most theorem, right? If you have like a co-compact group, discrete co-compact group, then nearby groups are conjugate. It's a local rigidity. And then the third thing, which is the analogous thing to dominated splitting, is a convex compact. Okay, which Francois talked about, and I will give a definition a bit later. So in the theorem, which he puts in the here in this block here, the theorem is the following. Maybe I can wait a bit to erase that. Theorem. Oh, these are the ones that don't work that well. Yeah. Oh, it means injective. For the people that do group theory, they call it, when it's a morphism, it's injective. For, like you have a copy of gamma inside the, that just means that the kernel is trivial or it's injective. Injective. Thank you. Injective. Terminology. And so the theorem from this paper of Sullivan, 1985, is if F is, sorry, I was looking at the theorem below, if gamma is structurally stable, so it's stable, yeah, structurally stable, in PCL 2C, right? In PCL 2C. PSL 2C. And then either it is rigid, or convex co-compact. That's it. So maybe I should give a definition of convex co-compact. So, oh, I totally skipped. I was kind of embarrassed to talk about dominated splitting in front of so many experts. So I kind of skipped something I wanted to say, which is that this condition here, it's really, like, I think there's no way getting around it. It's pretty ugly. But there are really nice ways to say it, which are more recent. So I should talk about that first. Okay. Or maybe I should just say, yeah, okay, I didn't look at my plan, and I skipped this thing. So I should say that, yeah, just right here, maybe. Bocci and Grumelon, they give a nicer, Grumelon, show that like the dominated splitting thing is an if and only if, a much nicer condition, which is that if you look at the singular value, so I have to check which one is going to be smaller. Okay, I plus 1 of dxf n divided by the singular value I of dxf fn. Then this thing will be exponentially small. Okay, maybe not the same constant c and lambda, but and the singular values are whenever you have a linear map between two spaces within a product, they're just the square roots of the eigenvalues of the map times its adjoint. So they are the sizes of the axi of the ellipsoid, which is the image of a unit sphere. So here it's like, maybe I'll do it in dimension 3. Okay. Or I could write dxfn. And you get some ellipsoid, and it has a major axis, and then it has like a middle one, and then it has the smallest one. And these three lines, like the lengths of these three things are the singular values. So this one is the norm. S1 equals the norm. S3 is pretty easy to write. It's so I put a map in R3, right? Dimension equals 3. S3 is like the inverse of the norm of the inverse. D f n x f minus n x norm inverse. And S2, you can figure it out. But so it's just the really natural numbers whenever you have a linear mapping that tell you the axi of the ellipsoid. And watching Rumulon show that, in fact, you don't have to bother with constructing the splitting and all this. You just have to check the singular values. And so my definition for convex co-compact, gamma is convex co-compact. Oh. Co-compact. So the definition, if it is finitely generated, and you just look at the singular value. So I can write it much easier here. Norm of gamma square. Okay, minus 2 to make it the same as over there, which is the second singular value of gamma divided by the first one. And it has to be smaller than constant. And then you put lambda to the, there was a number of steps of times you applied f. Here it's the word length of gamma. So gamma is finitely generated, and you can pick some generator. And it's how many generating elements you need to multiply to get to gamma. So this is the word length of gamma. Okay? So essentially, that's the introduction to my talk. If anyone has a question right now, would be a really good time. Because what I want to do is try to see what can be said if you replace PSL2C by some other group. And this is within a context that also Francois mentioned of also representations, which I will talk about. But really, it's like, it's really, I put some lines below ongoing, because it's really like we have very few examples of these types of representations, and we're trying to study the very basic ones. So in a bit, I will switch to SL3R and talk about what examples we have, what we know, and what we don't know, and try to see what the analogous question to this Sullivan theorem could be in higher rank, so SL3 or more. So if anyone has a question, it would be a really good time. No? Everyone's completely lost? Okay, now we'll talk about 3 by 3 matrices, so it should be more or less simple to get back in the talk with you. Okay. So the question essentially is, okay, you have this theorem, and there's some analogy with dominated splitting, which I can make more precise because there are recent papers. And the question is, like, replace PSL2C by something else. What happens? So I'll give this definition of an Anossov representation. representation. Okay? And so what it's supposed to be, and more or less everyone is convinced that it is the generalization of convex co-compact when you replace Kleinian group with subgroup of 3 by 3 matrices, for example. That's what it's supposed to be. And the definition exactly corresponds to dominated splitting. There is some dominated splitting, okay? So I'll give, okay, I'm not going to get into any, I didn't even look at this thing. Okay. So here we are. All right. So, all right. So the setting is the following. You have gamma, some finitely generated group. Presentations. Group. Right. And you have some representation, so some morphism from gamma into, and let's put just what I will talk about, which is just some product, like you have some products from I equals 1 to n of some SLD I over R or C. Okay, or C. Why not? Okay, obviously there are more general ways of saying this, but since I'm going to talk about SL3, who cares? And then it's Anosov, is Anosov. Anosov. If for some I, so some of these factors, and J, some I will be between 1 and n, and J will be something between 1 and di minus 1. You have this inequality, right? The singular value, what do I have to write? J plus 1 divided by the singular value J of what? Of the, so you associate to each gamma some finite sequence of matrices, and you look at the jth one, pi j of rho gamma. And this quotient is going to be small. Okay, C is positive, and lambda is between 0 and 1. For all gamma, right? For all gamma. And I should say, because this is like a super, I ignored the work of many, many people, so I should say like a few words, at least. So they're supposed to be, or they are, I'll just say they are, higher rank, whatever that means, rank, analogs, oh, I don't know how to write this word, okay, of convex co-compact. Co-compact subgroups. Right? At least it looks very similar to this way, right, of writing it. And the origin is like, okay, so origin is in work of, I should write like Hitchin. So Hitchin was studying what happens when you put a surface group in SLD. You put a representation, and there's a particular component where all of the representations have discrete image, so it's really kind of weird. And so that's a remarkable result. And then several people were trying to understand what's special about those representations, that they are, the property that they are discrete is stable. And what happens is they are Anosov. So then it's Lauri, Benoit. And to get to the definition, okay, more people I should mention. Even I'm forgetting to mention friends, because to get to this definition, so the paper that I understand and read, I think it's actually due to first, what is it? Kapovic, Lieb, and Porti, but the paper I understand is Bocci, Gurmelon, and Sambarino. But just to get to this definition was already like a lot of work of many people. But now the definition is super, super analogous to dominated decomposition, and it's not just analogous, it's actually equivalent to there is some dominated decomposition on some cocycle, okay? And so the question is, can you prove some theorems, for example, that some stability property of the representation would imply that it has to be anosov? That would be like because here what he's saying is, if this thing is robustly injective, robustly faithful, then it's anosov, okay, because the co-compact case is also. And so the question is, does this work if I replace PSL2C with SL3R, for example? So that's the question, is that's the question. And the answer is no, but does rho robustly faithful? So the structurally stable in Sullivan's case, faithful, imply anosov. In general. In general. And so the answer is there's an answer, but it's like a lame answer, I think. The answer is no, but okay. And the reason, because there's a very simple reason why the answer is no, and it's because when you look at a co-compact group of SL3R, okay, that particular group does not admit any anosov representations. But on the other hand, it is structurally stable, so it is true that it's robustly faithful, this thing. Any nearby subgroup is actually conjugate. So that's kind of a lame answer. So the thing would be to try to understand, okay, more in detail. I have this group. I know that it admits plenty of anosov representations. And I look at some representation which has this stability property, which is like robustly faithful, for example, and I try to see, okay, does this imply anosov, for example, if it's into 3x3 matrices? So that's the question that I will now talk about for a little bit. I don't know how much time, more or less, I have left. Okay, good. All right. So again, if anyone wants to ask a question, now is a really good time to do it.
No, I have a question.
Yeah, thank you, José.
What I think is that you want to relate this thing with the stability conjecture, okay?
No, it's very analogous, like it's a.
On the other way,
Uh-huh.
okay?
Yeah, yeah.
And then the question is that, okay, in anosov representation, this would be the hyperbolic things in your work?
Yeah, in my.
Or you can get some other hyperbolic representation, not only anosov representation.
So there's like a very formal connection between anosov representation and dominated splitting. So there's an equivalence. It's like an if and only if. The representation is anosov if and only if I have this co-cycle and it admits a dominated splitting. That is, I should say, okay, that's the paper of Bocci, Potri, and San Marino. So I think what it shows is that anosov is equivalent to dominated splitting. That's what it is. And it's very formal, like the equivalence is
But you don't have any other thing like, okay, you take a hyperbolic set,
yeah.
then you don't have some connection.
As far as I can tell, the analogy more or less ends with this with this result.
That's it, okay.
Yeah. And the other thing that bothers me a lot, because since we're talking about the analogy, is so for hyperbolic dynamics, you had before the main theorem, before the stability conjecture and all that. Yeah. There is no, I know no analogy for other classes. So there's a theorem that this definition means this certain co-cycle is dominated. But there is no other analogies that I know of that other classes of differentiable dynamics. And I wanted to add also that in hyperbolic dynamics, and you guys had, before the theorems, many examples, interesting examples of attractors. Catherine mentioned the plicking attractor, solenoid, 2111. You had a bunch of examples before like any theorem. And here it's really strange, the situation, because so there's this family of examples by Hitchin, which is a certain component of representations of a surface group into SL3, for example. That component is well understood, and there's like several works. And then there's, as far as I can tell, maybe I'm speaking out of place, but there are very few examples which are well understood. Like a recent paper is to understand representations of a triangle group with like a very simple Fuchsian group into SL3, for example, in detail, like understand when it's a nonce, when not, which. So really there's a lack of examples, and so we're trying to explore the basic examples. Okay, so now I can actually state some results. Maybe? Yeah. All right. So, yeah. Okay. So we look at just, because there's so few examples, we just look at gamma free group, like free, non-abelian free group in two or more generators. So it's because why not? There are no examples, so why not pick the simplest thing? And the answer here, this no, is because the group that you're looking at doesn't even have any anosal representations, because it's a known fact. Also, I think that's Kapovich, Lipporti, that if a group has an anosal representation, it's a hyperbolic group, special class of groups. And so you need to start with a hyperbolic group. Why not the free group? Okay, that's a thing. And so a first result, maybe I should look at this. That's like a small extension, or I don't know, it's not even an extension of Sullivan. So again, with Leon. Maybe I should write over there, because it's okay. Let's erase Sullivan, in case the statement gets large. So the theorem with Leon and Rafael, like a sanity check, I think it's Rafael for the whole thing, is so this is it. Let gamma be a non-abelian finitely generated free group. Two generators, for example, I don't know. Rated free group. And rho, a representation. And we just keep the matrices 2 by 2. That's the, so you put PSL to R to a certain power, and PSL to C to some other power. Let's say. And suppose that it's stable in the sense of Sullivan, so it's robustly, I should say this. Okay, put up here. So the theorem is then rho is robustly faithful, so robustly injective, or I don't know, robustly injective. If and only if. If and only if. It is anosov. So this is like a mini result, and it's kind of like a sanity check for the idea that, okay, when your group doesn't even have anosov representations, this is false, but maybe like it's not completely worthless to try to do some analogy. So that's the first result, and then I can state. Okay, so this is like a mini result related to Sullivan's result. And So the what? Mini? Well, I don't know. I feel like we're really like, I like the work, I'm having a good time, but I feel like we're really like at the stage where you're trying to collect like examples and and this is like an example where you say, okay, I keep everything 2 by 2, but now there's 5 matrices instead of just 1, and you want to know that, okay, if you can't perturb to make this thing have a kernel, then actually one of these coordinates is actually like a co-compact, convex co-compact group, and it's a nice result. And then we can get to the things I would like to know. I don't know, Jagalini, how much? 10, great, okay. So we have one example and one theorem, which does not cover the example. So the example, we have an example of the type of thing you would like to know. And the example is the following. You take like a matrix A. So it's in, you take like a very large lambda 1, lambda 2, lambda 3, and put them like this matrix in PSL2 or just SL3, SL3 R. And then you take B, some conjugate. So it's going to be just some conjugate of something like this, like maybe I put 2 here. I could have put something explicit here, like I don't know, maybe 4, 2, 1/8. Why not? And then you put G some conjugate of this thing, and I have to put 1/4 or something like that, minus 1/4. Yeah, minus 4, minus 1/4, G minus 1. In general position. So this is like a super simple example. So, and general position means, okay, A is diagonalizable, so it has a splitting. And B, it has a 2-dimensional invariant subspace, which corresponds to the 2 conjugate complex eigenvalues, and one 1-dimensional subspace. And you don't want any of those to coincide or be contained in any of the others. That's the example. And so the thing that happens is that if you take a large power, you can do like a ping-pong lemma, and you show that like A to the n, B to the 2n plus 1. So you take a gamma like this, and it's free for large n. It's free for large n. For large n. So you can actually, you construct, it's a ping pong argument. You construct some boxes in the projective space. You have to be a little bit careful because, okay? But you construct some boxes where when I apply a new element, it goes, unless I'm in the repelling box for that guy, I go to the attracting box for that guy, and the norm of the vector grows. And so you do a ping-pong lemma. There are many variants of the ping-pong lemma, and this is one more. And you prove that it's free. And it's much more than just injective. So it's the title of the talk. And gamma is quasi-isometrically embedded. And gamma is quasi-isometrically embedded. And what does that mean? It means like the norm of an element gamma is like some, oh, I put it the other way around. Okay, well. Okay, the norm is some exponential in the word length, and now lambda is greater than 1, right? So if you, it really, there's some vector which is going to get very large if I apply a combination of these 2 elements with lots of letters. Okay, and so the question is this robust? Like, because this guy is gamma There are no Anoso representations. Near the inclusion. Because, so I totally erased the definition, but I think already it's interesting to just say something. And the reason is because when you have an Anoso representation, it's telling you that the first and second singular values will separate exponentially, but in SL3, the second and third also have to separate if the first two separate. So it tells you that if you look at the moduli of the three eigenvalues, they are distinct. When I take a very large power, they have to be very separated, these three singular values. And if I had a matrix like this, then that doesn't happen. There's going to be two which are very close together, which correspond to this eigenspace for the complex eigenvalues. So if you have something like this in your image of the representation, it cannot be Anoso. That's what I'm trying to say, basically. You can't have complex eigenvalues if it's going to be Anoso. And this guy, so the question is, can you perturb, like, okay, now someone gives you these two matrices, A to a large power and B to a large power, and can you move them a little bit and make it so that it's no longer injective, this representation, or at least no longer quasi-isometric? Can you do that? Well, we don't know. So that's a question. Is it robust? So even less than, we don't know if robustly faithful implies Anoso. We don't even know if robustly quasi-isometric implies Anoso. And we have no technique to perturb this and make it non-injective. So we can cheat. I think we will cheat. We can make some example similar to this with more matrices. And if you have more matrices, it's easier because you have like free variables you can perturb. And so you can make some similar example, which you can then prove is not robust by perturbing the third matrix you added. Or, okay, this type of thing we can do, but really, like, this is super basic. And I have really no idea how to do this. And so if I have a little bit more, 5 minutes, I can before admitting complete defeat, just state a theorem where we have a positive result. But really, I would like to know this. This is what I would like. This is too easy not to be able to know this, but apparently it's somehow out of reach so far. And so maybe to leave with actual results and not just hopes, I will erase this thing. And so there's a class of examples which are much simpler than a general representation into SL3, and which have been studied recently. So I want to say, okay, someone else chose a name for me, but okay, I will choose my own name. I call them derived from Barbo. From Barbo representation. Barbo representation. So, and there is some, also there's some work I should mention. Max Lann, he studied this type of example, and so we get a result in this type of example. And so what are they? They're the following. You first pick two matrices which are 2 by 2, like you pick A and B. I don't know, you pick A, some very large lambda minus 1. Lambda's very large. And then you pick B to be like the conjugate by the rotation of 45 degrees to this guy, like A. So A has, sorry. A has, I put unstable here and stable. And B, they're just rotated like this. What is it? Like this. Okay. So if lambda is very large, they generate a free group, right? Gamma is free. It's a convex co-compact subgroup of SL2R. And so you do like a trick. You don't understand SL3R, so you say, okay, I'll stick to what I know. 2x2 matrices. And I put them into SL3R, but in a way that I can still do 2x2 matrices, which is what I know. So how do you put them in? Barbeau studied if you just put like the row of gamma, so row from gamma to SL3R. Barbeau studied, okay, what if I just put row of gamma, putting gamma here, and then something, right? And then the variant you can do where you perturb, instead of having this hyperbolic matrix, you can multiply by homotopy and make it like an attracting point with a strong, stable. And you can do that like this. You pick a lambda perp of gamma, and then you have to put the square root of the minus square root. And so you still have 3x3 matrix of determinant 1, but now there's the preserved plane, so the plane with vectors x, y, 0. Instead of acting like gamma, you act like gamma over 1 million, I don't know, something like that. And so you put some zeros here, and here you can put whatever you want. And the nice thing is that the lambda is a morphism, so lambda perp of gamma eta is the product. And up here, it's a bit uglier, but it's like a co-cycle. It's not that bad. And so you're basically, it's some family of representations into SL3R, where you can study it by looking at 2x2 things. And it's really nice because, so if here you put zeros, okay, I don't know how much time I have to say some. -1, oh, okay. All right, so I just state the theorem, and then, so the theorem again with Leon and with Leon and Rafael. I'll just state the theorem and then here, sorry for going overboard. So the theorem is, so these guys are, they are robustly quasi-isometric if you perturb within the plane. Okay? In fact, it's if and only if. You have to put a convex compact here. So the question is, can you perturb without preserving the plane and destroy this thing? And the theorem is yes. So the theorem is rho is robustly quasi-isometric if and only if it is an OSOF. So it's like we get some positive result for a special class of representations. And the cool thing, just to finish, is that if you only perturb within this class, then it's robust. So you have to really find some perturbation where you destroy this plane, and it's really hard to do. Like things get out of hand really quickly when you no longer preserve the plane. So that's my talk. Sorry for going over time.